So apologies if I'm reading from a script. I'm 26 and my memory's going. So my name's Tom Watson. I'm a pottery researcher based in Dundee. If you can't tell, that's not where I grew up. This talk will be on a project investigating whether characterization of medieval pottery, or any glazed pottery, can be achieved objectively through analysis of the colour hues of sherd's glaze. This is called the GCA project, which GCA stands for Glaze Colour Analysis. This has been carried out over the past few months, mostly by myself in Scotland, with assistance from Anne Jenner at York Archaeology Trust, and some funds from the AXPA Resilience Scheme. The idea for this project came about as I was writing my master's dissertation. I was investigating whether the glazes on two pottery wares were chemically distinct. As a small aside to this, I used photographs of the sherd's glazes to objectively show that an overfired example of one ware was visually distinct from a darker glazed example of another ware. Afterwards, I wondered whether this technique could be expanded to include a wide variety of sherd types, and whether each glazed pottery ware had a different colour hue. So this is how the technique primarily functions. A glaze sherd is photographed under standardised conditions, and a 1 centimetre target area of the sherd's glaze is isolated. Its colour averaged using a computer program, and its RGB code then recorded. And if the ware has already been determined, it's added to a database. Just in case you're unfamiliar with what an RGB code is, that stands for red, green, blue, and is used for electronics such as computers or modern televisions to produce very specific colour tones. So I'll just briefly go over the aims of the project. And just bear in mind going forward that this is not to create a product for market. This is an experiment to determine whether this principle works or not. So primarily the aims were to produce what was coined a light chamber, which would produce the standardized lighting conditions the technique required. Once this was produced, the aims were to ensure that these conditions were standardized to an optimal degree, ensuring that any results gathered were as accurate as could be made possible. In addition, in order to ensure that this technique can be potentially applied to elements of the heritage sector, if a successful technique is produced, a few caveats were introduced. Partially due to budget constraints, but also in order to maximize accessibility of the technique. The chamber needs to be made from widely accessible materials, from designs that can be transferred digitally. Any power supplies needs to be self-sustaining, as I know from experience. Finding a plug socket in an archaeological warehouse is impossible. It needs to be usable without the need for specialist camera equipment, again mostly because I couldn't afford it, but also for accessibility. And it needs to be usable by someone unfamiliar with the project with minimal training. So with this in mind, I initially designed the chamber on a 3D designing program with the idea that it could be entirely 3D printed. However, after consultation with a few 3D printing companies and Dundee University, who eventually ended up helping me manufacture the chamber, it was decided to produce it primarily from MDF, with electronics mounted onto PVC in order to ensure it doesn't become a fire hazard. The chamber had to be slightly redesigned to allow for more traditional carpentry fittings, and a couple of things you can see on screen were later scrapped and modified, either because of a later redesign or just because of impracticality. So after a 2-week delay during the Scottish winter, the chamber did eventually get made. This involved using a rotating drill to cut the intricate grooves into the MDF, Some 3D printing was needed to make sure to make some of the more unusual shapes. A finer drill bit was needed to cut the camera hole into the PVC. Overall, I estimate the chamber to be comprised of about 90% MDF, 7% 3D printed plastic, and 3% PVC. Now, I'm not a carpenter, so it did take quite a lot of time to chisel and hammer everything so it all fit together. But once the framework was complete, the next priority was just to get the electronics wired, making the chamber ultimately functional. Now, the individual in the shot is not myself wearing a wig. This is my friend Luke Rutter from the University of Sheffield's engineering department, who was able to wire up a relatively simple circuit, including a long-lasting battery, leading into 4 LED lights surrounding the camera hole in the interior of the chamber. We also included a voltage regulator in order to ensure that as the battery dies, the light stayed exactly the same brightness. Once the chamber was made, an initial test was conducted that highlighted a problem, not with the chamber, but with my smartphone, which I was using to take the photographs. Problem was that my phone was being a bit too smart, as it would adjust the brightness of the photo based on the size, colour, and particularly the lightness of the shirt. I see the one on the right, obviously the background's a lot darker. In order to address this problem, as well as maximise the accuracy of the technique, 4 tests were devised, the first of which was the camera test. This involved experimenting with 4 different camera settings and analysing the standardised background across different samples. These are some of the photographs produced for analysis. At first glance, there doesn't appear to be much variation, but analysis of the RGB codes of this standardised background did produce a winner, which was setting 2 in this chart, and which means it has the least variation across all shared samples. There were 5 reps of this, these weren't the only ones. Sorry, I was meant to show you that earlier. The second one was the background test. Using the setting from the previous test, tests on which background would produce the most consistent results with the least variation were conducted. These are the 6 different backgrounds that we tested, just to get an idea of what type of background would produce the most consistent results. From the top left clockwise, that's colour checkerboards, black and white rings, white, black, colour rings, and checkerboard. Once again, a small white target in the top left of each image was included in order for the results to be comparable with each other. Only a large white and a small black shirt were used for this test, as these 2 were the most distinct in RGB codes based on the previous test. The results weren't quite as clear-cut as with this one, but when we looked at the statistics, we concluded that the colour checkerboard pattern was the most consistent, the one that kind of looks like LV alpha. However, I should mention that these results did take a bit of time to process, and we didn't actually have it ready for the next 2 tests, so it was actually checkerboard that went forward for the next ones. According to the next one, the watertight test, as this is a test to ensure that results are not distorted by exterior light entering the chamber. To do this, I placed the chamber by a south-facing open window and took readings hourly from 4 AM to 11 PM. It wasn't a nice day. Now, it was quite a sunny day for Scotland, so the light levels hitting the chamber didn't fluctuate very much. But as a result, show a small amount of light did enter the chamber while it was off, although not while it was covered up. While the chamber was switched on, however, we didn't see much of a change in light levels while the chamber was covered or uncovered. These are the resulting photographs across the day with the chamber on. The row above with the chamber uncovered and the row below with the chamber covered. And these are the same with the chamber off. If you magnify the differences with the chamber on, you can see that the two variables follow each other very closely, with the covered data producing a couple of unexplained spikes. For this reason, it was concluded that any interference from exterior light sources was negligible. And the important test was the grouping test. The grouping test would determine how well the technique would work as designed. This involved gathering 71 glazed pottery sherds and a few staying in for good measure, and analysing the RGB codes of their glazes. This is just to show you what the colours of each of these images would look like averaged. I'll come back to this a bit later. So these results were plotted on a graph using what I'm told is a PCA test. These dots don't make very much sense by themselves, but once joined up, they form distinct groups, here represented by the bubbles. Now, this was initially quite encouraging to see, as most of the wares are quite distinct. But the challenge will be to significantly reduce the amount of overlap in the green wares group, just towards the centre there. Although naturally some overlap was expected at this stage of the project. Well, these distinctions could form the basis for a database comparison, allowing an unknown sherd to be potentially characterised based on its position on this graph. The aim will be to increase the amount of data put into this graph before we can go through that, though. Just so I mention it, I should say that these sherds were supplied by York Archaeological Trust and were excavated primarily in Yorkshire. So I'll just talk about where the project will be headed in the future. So the following two slides are just there to show you the difference between one average glaze reading and two average glaze readings, or this is essentially splitting it, which I think is going to be a lot more accurate. Because we can do this with up to 10 different colours on any individual image, potentially increasing the accuracy tenfold. But just to show a few more further tests we're going to do, an investigation will take place as to whether measuring the differences in RGB codes can help get a more accurate grouping. Again, just to try and reduce the size of those bubbles. I'll also be looking at whether analysing the whole sherd rather than just a 1 centimetre target area will produce more accurate results. In terms of plans for the project, I'll be looking to bring in a programmer at some point to help me make the process a bit more autonomous. I can't say that. A bit more automated. As I feel that a major drawback of the project is, so far, is while the photography of the sherds is actually, it takes very little time, processing these photographs is very slow going. So if further tests prove successful, I'd also be interested in increasing the sample size, potentially building a wide database encompassing a large variety of RGB codes for comparison. If enough interest is garnered in this technique, I may decide to distribute it for use. So I'll just go quickly through how this could be applied to the heritage sector. Although this is assuming the tests and developments go amazingly well. This could potentially help archaeologists, specialists, and museum researchers quickly analyse and characterise large glazed assemblages, allowing access of information about pottery waste quickly and easily. In terms of wider accessibility, this could be used as an informative tool to reinforce outreach schemes or even the portable antiquity scheme. It could be used in the same capacity in schools or universities. However, if not much comes of it in the end, it's quite a good device to produce some good quality images of sherds quickly. Just say thank you to the staff at York Archaeological Trust, in particular Angiana, who helped me get the project going, as well as Lorna Coyne at Dundee University and Luke Rutter at Sheffield University. If you want to keep up with the projects as it progresses, I semi-regularly update the project blog, gcaproject.wordpress.com. Thank you. Any questions?
You mentioned glare as a potential problem in analysis.
Yeah.
How big a problem do you think that is? And have you got any ideas about how to reduce it?
Glare at the moment is not a problem because I'm using a 1 centimetre target area. I don't have a photograph on me, but if I have, actually I might do. 1 second. Sorry. There. If you can just see this kind of square of light, that is the light around the camera lens essentially. I would target an area in the middle there. If I were to use the whole sherd, that glare could potentially be a problem. Currently it isn't. That's why I would need to look at ways of reducing that. They're not pure LED lights as well. They're I forget the name. We put a strip of something under there to stop as much glare coming through. Diffusers. Thank you.
Does it matter which area of the sherd you pick? I'm just thinking of humblewares, where you get that lovely ambery colour around the edges.
Well, if I'm targeting something, I tend not to go to edges of places if you can see it. Just because I don't want it to be too thin and the actual fabric is going to come through. So we try and go to particular areas where possible, but we might need to look for another solution we can find doing whole sherds.
Is this your first time at Heritage?
Second time.
Is it, can I ask, how does it work on sherds that are degraded, so where the glaze, where the sherd's been knocking around for a long time, the glaze is?
I do try and avoid picking those, which will bias it towards fully glazed ones, but I think if we start splitting the colours further and further, that will potentially reduce that problem.
What didn't mention much about the stamium. What did you find that they were very closely clustered, or maybe I just missed that bit?
I didn't point it out. Probably should have. Sorry.
Could it be used on the bare fabric, if you like, or like slipped things?
Depending on how well it goes for glazes, if it's very, very accurate to the point where you can even pick between production sites, then I might consider going into fabrics. But I think fabrics are a bit homogeneous for it at the moment. But stamium is that little orange one at the top there.
Any more questions at all? No, brilliant. Thank you very much, Tom.